This is 4.4 wave interference and standing waves. It's all part of the wave outcome number 1, investigate the properties and characteristics of 1, 2, and 3-dimensional waves. So in this lesson we will learn how to illustrate constructive and destructive interference of waves, including the principle of superposition and standing waves, and how to solve problems related to constructive and destructive interference of waves using the correct number of significant figures. So wave interference and standing waves. When two or more waves act simultaneously on a medium, interference occurs. So that just means that one wave is traveling towards another wave and they meet up. So the principle of superposition occurs right in the middle where they happen to run into each other. So that states when two or more waves pass through each other, the resulting disturbance at a given point in the medium is found by adding the individual displacements each would have caused. So you'll be adding this displacement and this displacement. You'll be adding those two together to come up with the superposition of the wave. So note that displacements below the rest position are considered negative. So troughs are considered negative, and those look like that. So these are negative. There are two types of interference when two waves are superimposed: constructive interference and destructive interference. So constructive interference occurs when the resulting disturbance is larger than the individual disturbances. So this process occurs when two troughs, or two crests, or two troughs meet. So in this example, we have A and B coming together, and when they add together, they result in a larger disturbance, because it'll be A plus B. And then afterwards, they just split off. A will continue in its direction, and B will continue in its direction. And destructive interference occurs when the resulting displacement is smaller than the individual displacements. So this process occurs when a crest and a trough meet. So we see that A is the trough in this situation and B is the crest. When they meet, you're just going to have A minus B. And it kind of looks like B goes up 2 and A goes down 2. So you're just going to have 2 minus 2, which is going to be 0. And that's why there is no wave right here. It just balances out. And then after superposition, B goes its own way and A goes its own way. So an example, the two waves in the before pictures are traveling towards each other. Draw a snapshot of the superposition of the waves and also what they look like after superposition. State whether constructive or destructive interference is happening. So I will draw the snapshot of the superposition in red. So if we have a crest coming towards a trough, we know that we're going to have to take the displacement of the crest and minus the displacement of the trough. So we'll see that there's a displacement here of 2 and a displacement here of 1. So our superposition is just going to be 1 up, because 2 minus 1 is 1. So that's what our superposition would look like. After the superposition, I'll draw that in blue. After the superposition, the waves just continue on doing their thing. So after they meet up, this one at the bottom here is just going to continue on. And this one, this crest up here, is just going to continue on its own way too. So that's going to just keep going that way, and that's going to just keep going that way. In the bottom example, we have two crests meeting up, so we're going to have to add them together. So we will just, so this is 2 up and 3 across, and this is 1 up and 1 across. So we will add those two together, and we will end up, you go 2, you add those together. So that's what our superposition would look like for that one. After superposition, the waves would just continue on. So this wave right here would continue going left, so it would continue going that way. And this crest right here would just continue on going that way. It also asks us to state whether this is constructive or destructive interference. Remember, destructive interference refers to when the superposition is smaller than the initial disturbances. So when that superposition is smaller, the disturbance is smaller than the initial disturbances, it is destructive. So this first one is going to be destructive. And the second one, constructive interference, happens when the superposition displacement is greater than the initial displacement. So this is going to be constructive. This is another interactive wave simulator that you can go and access it on this link anytime you want some extra help. So, standing waves. In a one-dimensional medium, a string or a spring, if the amplitude and wavelength are just right, a standing wave can be produced. For the purposes of this lesson, we will be imagining a string fixed at both ends. So for example, a guitar string. A standing wave is actually an interference pattern consisting of both maximum constructive and destructive interference. What happens is multiple waves are created in one direction, and this wave then reflects off the fixed end and travels back the way it came. So you can think of this red wave is just going in this direction, and once it hits this fixed position here, so it's traveling in that direction, it reflects back to this fixed position, and it just keeps going on and on and on. We'll also see these points where they meet in the middle are called nodes, and these parts on the ends, so at the crest and at the troughs, are antinodes. So meanwhile waves are still being produced in the original direction, these waves traveling in opposite directions interfere with each other. So however, it's only considered a standing wave when the wave interference is in such a way that it appears as if the wave does not move along the string. The places with destructive interference are called nodes. Nodes are at the rest position. So right here would be all your nodes. The place with constructive interference are called antinodes. So antinodes look like the crest and troughs. So they're all right here would be your antinodes. So that's just another interactive that you can play with to look at standing waves. If you change the frequency of the wave, you can alter the separation of the nodes. So the following conditions must be met for a standing wave to exist. There must be two waves of the same frequency. One or both must be a reflected wave. There must either be a whole or a half number of wavelengths in the pattern. So for example, 2 wavelengths or 1.5 wavelengths, but not 1.9 wavelengths or 3.25 wavelengths. So you'll see in this example, the most common one, we know that the distance between crest to crest or trough to trough is 1 wavelength. So if we look at this wave, we know that a wave, this particular wave is moving, and then it hits this fixed position, and it is reflected back. So blue is traveling this direction, and the red is traveling in that direction. So there's one wave, that's the incident wave, and one reflected wave. So we know that the distance right here between these two troughs is 1 wavelength. So we can call the distance between each antinode 1 wavelength divided by 2, because if you met right in the middle here, it would just be half of a wavelength, half of 1. So you can see that. So that's why when they ask you for between the antinodes, it's going to be your wavelength divided by 2. If they ask you for between your node and your antinode, antinode, it's going to be your wavelength divided by 4, because if you were to cut this again, it would end up being 1/4, 1/4, 1/4, and 1/4, which would equal your 1 wavelength. And these two halves added together would also equal 1 wavelength. So that's where those numbers come from. So the second point is because the endpoints of the wave must be a node, which cannot exist in any other lengths than in a multiple of 1/2. So the number of nodes and antinodes as well as the length they are apart will be useful information to help us determine the wavelength. So these will always be the information that we're going to use in our questions. So an example, what is the wavelength if the distance between the node and the antinode is 8.35 centimeters? So if we have a wave that travels and then hits a fixed position and is reflected back off that fixed end, and it just keeps going like that, this question is asking us, what's a wavelength? So what's the distance here? If we're given that the distance between a node and an antinode is 8.35 centimeters. So what we can do is we can say that 1/4 of our wavelength is equal to 8.35. Because if we were to split this up into nodes and antinodes, we'd notice that we have 4 positions. So 4 spots. So that would end up being, so each spot represents 1/4 of an actual wavelength. So that's what we would use as 1/4 of a wavelength is equal to 8.35 centimeters. So if we times 8.35 times 4, we're going to get 33.4 centimeters as our final answer. In this example, what is the speed of a wave if the distance between 2 adjacent antinodes is 12.5 centimeters and its frequency is 375 hertz? Okay, so we need to find the actual wavelength. So we're just given the wavelength between 2 adjacent antinodes. So if we look at a standing wave, so we have a wave that hits a fixed position and is reflected back. And what the question is wondering is, what's the difference, what's the wavelength if the distance between 2 antinodes, so here and here, if this distance is 12.5 centimeters. So if we were to split this up in antinodes, we would end up having to split up the wavelength in halves. So to calculate the actual wavelength, it's going to be half of the actual wavelength is equal to 12.5. If we times 12.5 by 2, we're going to get 25 centimeters. And now we can calculate the speed of the wave by using the universal wave equation. So we just figured out that our wavelength is equal to 25 centimeters, but we have to convert that to meters. So it's going to be 0.25 meters. And we are also given that its frequency is 375 hertz. And we are trying to find the speed of the wave, so the velocity. And that's going to be measured in meters per second. Okay, so if we write out our universal wave equation, velocity is equal to frequency times wavelength. It's going to be 375 multiplied by 0.25. And when you multiply those two together, you're going to get 90. If we check our question for significant figures, see that there's 3 here and 3 there, so our final answer has to have 3. And we check our units, it's going to be velocity, so it's meters per second. So this wave is traveling at 90 meters per second. Another example, the number of waves in a standing wave pattern can be found by subtracting 1 from the number of nodes and dividing by 2. So likewise, the number of waves can be found by dividing the number of antinodes by 2. So that's key to know. Waves generated at point A are reflected at B to produce the standing wave pattern shown below. How many antinodes are there in the pattern? So just like it said below, or above, sorry, the number of waves can be found by dividing the number of antinodes by 2. So we can say that the number of antinodes in this problem is 1, 2, 3, 4, 5, 6. So there's 6 antinodes in this pattern. And what is the wavelength produced in this pattern? So if we consider that one wave is traveling till it hits a fixed position and then it's reflected back, the question's asking us, what is the wavelength produced? So what's the distance here? And the only thing that it gives us is that the distance between the 6 antinodes is 6. And like I said before, that it reads up above, the number of waves can be found by dividing the number of antinodes by 2. So if we go 6 divided by 2, we're going to get 3 wavelengths. So we know that the 3 wavelengths are equal to 12 meters. So that's what the question tells us. So therefore, if we go 12 divided by 3, one wavelength is going to equal 4 meters. And that would be our answer right there.